final movie in a 3-part series about this question, which you can download from the link below. In the first movie, we made sense of the information that we're given in the question and we answered questions 1 to 3. In the second movie, we answered question 4 using a focus on force. And in this movie, we again answer question 4, but this time we focus on energy. Make sure you have watched those previous 2 movies first, because this movie builds on those previous movies. Also, remember that you can find many resources to help you learn natural and physical science on my website, www.learnscience.coza. And don't forget to subscribe to my YouTube channel. So, we're going to calculate the power dispersed by the engine using energy. Power is the rate at which work is done, work per time. So the power delivered by the engine equals the work the engine does, divided by the time to do that, which we're told is 15 seconds. So if we can find out how much work the engine does between B and C, we can answer this question. We know from the Work-energy Theorem that net work equals change in kinetic energy. We know that in this case, the change in kinetic energy is 0 because the mass and velocity of the car are the same at B and C. And that means that the net work on the car is also 0. What is net work? The sum of the work done by all the forces acting on the car. So we need to go back to our free body diagram to remind ourselves of which forces are acting on this car. The engine, which is what we're really interested in, friction, the normal force, and weight. What does the work-energy theorem say? It says that the net work done is equal to the change in kinetic energy. Now we know that in this particular situation, the change in kinetic energy is 0 because the mass hasn't changed and the velocity hasn't changed from B to C. So, all the work done by the individual forces together adds up to 0. So what are the individual forces that are doing work? There's work done by friction. There's work done by the normal. We take each of these forces in turn, you see. There's work done by gravity. In other words, the weight. Weight is a gravitational force, so let's say by gravity. And what we're really interested in, there's work done by the force of the engine. And all of that adds up to 0. Right, so now we need to understand work better. How is work done? Work is done when force acts through a displacement. Both force and displacement are vectors, and so they have directions, and the angle between their directions affects the magnitude of the work done, and it determines whether the work done is positive work or negative work. We can see that in this equation, work equals force times delta x, which is displacement, cos theta. Theta is the angle between the force and the displacement vectors. If the two are in the same direction as one another, then theta is 0. Cos 0 is 1. So this equation simplifies to work equals force times displacement. If force and displacement are in opposite directions to one another, then theta is 180 degrees. Cos 180 degrees is negative 1. So then this equation simplifies to work equals negative force times displacement. If force and displacement are at right angles to one another, then theta is 90 degrees. Cos 90 degrees equals 0. So in such a case, the force does no work. Now, Let's look at each of these forces and see how their directions compare to the displacement the car undergoes up the slope. As we do so, remember that work is a scalar, so these signs don't mean direction. Rather, positive work means that the work done increases the energy of the object. Negative work means that the work done decreases the energy of the body. Kinetic friction always does negative work because it always acts in the opposite direction to the displacement undergone. We see that here too. Friction acts down the slope as the car moves up the slope. Previously, we calculated the displacement that the car undergoes from B to C. Displacement equals velocity multiplied by time. 2 meters per second up the slope multiplied by 15 seconds equals 30 meters up the slope. We were told that friction force is 50 newtons. We know it acts down the slope, so the work that friction does is 50 times 30 cos 180 degrees, which is negative 50 times 30, which equals negative 1,500 joules, which means that friction removes 1,500 joules of energy from the car as it moves from B to C. The normal force acts at 90 degrees to the displacement, and so it does no work on the car as the car moves up the slope. So we can immediately simplify this to give the work done by the normal force is 0. All right, from what we've said, look, we can go and actually substitute the full thing in, and that's probably a good idea. But can you see, we can also use our brains. Work done by friction is going to be negative 50 times by the displacement. Now, previously we've seen that displacement is 30 meters. And so, if you like, you can rather do it in the full form, 50 times 30 cos 180 degrees. And that is the same thing as minus 50 times 30. So, it depends how complicated you want to be. The same story here. You can actually, well, we don't know what normal is, but times cos 90 degrees, and that equals 0. So, why not just use your brain and just say plus 0 from the beginning? All right, then what about the work that gravity does? So that's a bit of a tricky one. I'm coming to that. We need to figure out how to get this work that gravity does. But before we get to that, remember, work done by the engine is what we actually are interested in. So let's get it on its own side to make it the subject of the formula. So that equals minus work done by the engine, or by the force of the engine, doesn't matter. So what we're missing here is the work done by gravity. Now, there are 2 ways that I want to show you that we can work that out. Right, so now how do we find out what the value is of the work done by gravity? There are 2 ways in which we are going to do it. The first way, we are going to focus on the fact that weight is a conservative force, meaning it is path independent. So we're just going to focus on the starting and ending points, not the path that it took, which was to go 30 meters. And also, we're just going to focus on the vertical starting and ending heights. Why? Because weight is a vertical force. And we know that the ending height is 13,12 meters higher than the starting height. Now we know that the formula of work is force times displacement and then times cos theta to factor in the influence of direction of these 2 vectors. And the force here is weight, gravitational force. And then this one here we're going to take as height rather than the path length. And then cos theta between weight, which acts downward, and the change in height, the change in position, can you see that cos theta then is 180 degrees? Why? Because the force of the weight acts downward and the height was a rise. The change in height was a rise. So the two vectors are acting exactly opposite to one another. So that's why we are going to get a negative answer here, because cos 180 is minus 1. So the force of weight, well, we know what that is, 200 times 9,8. The force of gravity, which is weight. We multiply by delta H. We know what delta H is, 13,12 meters. It's 13,12 meters higher at the end of this interval that we're interested in than it was at the beginning. And then we multiply it by cos 180. In other words, this all becomes negative. We do this on our calculator. Our answer is minus, don't forget the negative value, 25,715,2. What we were busy calculating, the work done by gravity. Work is measured in joules, as is energy. Another way to see what we've just done here is to realize that whenever work is done, energy is transferred or transformed. Energy is changed. When weight, which is a gravitational force, does work, then gravitational potential energy is changed. If we calculate the change in gravitational potential energy, then we know the amount of work which must have been done. Change in gravitational potential energy equals final mgh minus initial mgh. Since m and g are constant here, that equals mg delta h, which is 200 times 9,8 times 13,12, which equals 25,715,2 joules. That's a positive value, because the car's gravitational potential energy has increased. Since weight acts downward, for there to be an increase in gravitational potential energy, something must have done work on the car against gravity. So put another way, gravity did negative work on the car. When a conservative force, like gravitational force, does work on an object, it causes a change in the potential energy of the object. For example, a change in the gravitational potential energy of the object. I said that we're going to calculate the work done by gravity in two ways. So this is the first way. Right, so in the second method that we're going to use, I mean, you only need one method, but let's just come at it from different angles. In the second method that we're going to use, we're now not going to think about the height as being the displacement undergone. We're going to think about this 30 meters as being the displacement undergone. And that is parallel to the slope, and therefore we must use the parallel component of weight. So weight parallel to the slope multiplied by the displacement parallel to the slope. We can say, yeah, cos, what is the theta in such a case? Well, the weight parallel to the slope is acting down the slope, parallel to the slope, but down the slope, which we're taking as negative, whereas it's actually moving, this object is actually moving up the slope, positive. So the displacement and the force are opposite to one another. So that's 180 degrees. So can you see, again, we're going to get this negative factor because cos 180 degrees is minus 1. In the previous movie, I explained the reasoning of how I found that weight parallel equals W sine theta, which is 200 times 9,8, which is weight. And then sine theta is 13,12 divided by 30. It comes from the geometry here of this triangle, but you can watch that other movie to see in more detail where I got that from. But here we're just simply going to apply that. So weight parallel, 200 times 9,8 times 13,12 divide by 30. And we need to multiply that by the displacement. The displacement in that same plane parallel to the slope. So that's 30 meters. And then times cos 180. In other words, times minus 1, I'm just going to simplify by saying minus. All of that is minus. Can you see that 30 and that 30 cancel one another? And can you see then we are left with exactly the same calculation that we had just now? And I was just trying to show you that we get the same answer two ways. So now what we can do is put this value in here. The work done by gravitational force is minus 25,715,2. Right, so now we can do our algebra. All of this is equal to minus W engine. So obviously we're going to have to change the signs. We can actually do that even now. Take away that minus. And this is just 0. So we can remove it and change that minus to a plus. And remove this negative. So now everything is just going to be positive, which might be easier on our calculator. We find our answer of W engine. We can write it on this side if we like. 27,215,2. What were we finding out here? Work done by the engine. What is work measured in? Joules. Is that the end of our answer? No, we were not asked how much work the engine did. We were asked the power of the engine. So we still have another step. Power is equal to work per period of time. Power of the engine is this value that we have on our calculator. Don't clear it. Divided by the time period that it took to do this work, which we're told was 15 seconds. So we simply take the value we have on the calculator, divide by 15, and we get the same answer that we got with the other method. And sure enough, we find the same answer as we had found with the force-focused method in the previous movie. So a quick recap of what we've done here. From the work-energy theorem, we know that the net work done on an object equals the object's change in kinetic energy. We know that for this car, that equals 0. We have the information needed to calculate the work done by each of the forces acting on the car except by the force of the engine. So we can use that equation to calculate this one unknown. Once we know the work done by the force of the engine, we divide that by the time taken to do that work. And we have the answer, the power delivered by the engine. And that brings us to the end of this series of 3 movies. I hope you'll re-watch parts that you're still not so sure of again until you're able to explain these concepts and their relationships to one another in your own words, and you can answer all these questions successfully, preferably from more than one angle.